So, we are going to begin the one of the most important topics in the course for the mathematical reasoning part, for the and applications part, and the overall lifestyle thing related to math. This is the most important thing, though there are more applied stuff, like more topics with more practical applications. But this is more of the for your linguistic, for your communication skills. This is the most important thing in this course. Okay. So, what is a proof? So, and I'll give you more examples of why do we need a proof and what kind of proofs methodology do we have. But let's talk about what is a proof. Okay. Just like as the name suggests, the English language name word proof, it's an argument that convinces someone about the truth of a proposition. You make a proposition, you want to say that this is a true statement, the proposition the truth value of the statement is true, so you use something called a proof. Okay? So, it's an argument. Of course, there has to be some rules for that, what is a valid argument, what isn't a valid argument. And okay, so let's just begin with some applications of proofs that we talked about earlier in our first lecture. Why would you need a proof? So, every time you come up with a solution to a computational problem, an algorithm, you design, you write a code for a computational problem, or you design an algorithm that an engineer is going to implement, you have to convince the customer, the professor, the TA, that the proof, that algorithm, the solution is correct solution. Okay? Depending on the application of it, it should be very clear that just writing code for it isn't a solution. A good solution, actually any solution, must have an associated proof that convinces the customer that that is actually going to solve the problem, right? So, it meets the requirement specification and it does what it is supposed to do, what it was required to do. Otherwise, without a proof, without a convincing proof, depending on what type of application that your algorithm is going to be used for, it could be actually life critical application, right? You write a small code for robotic surgery, you can't just implement it, it's going to waste a lot of time, and then it's going to have a much higher cost when it's run and there is a bug in the proof, in the algorithm, right? It's not supposed to do. And I could give you examples of where have these type of failures, what was the cost associated with this, life cost and the money cost for very simple flaws in a code, right, in a programming solution for this thing. So, you need to prove that your algorithm is correct, and this algorithm is correct is a proposition, right? It's a predicate about an algorithm. You are describing a property of an algorithm, that this algorithm does what it was supposed to do, what it is written in that requirement specification, and that's a statement that needs to be proven. Okay? So, another statement we want to make about our computational solution is that the required resources for my solution is this much, right? It takes this much time. It will give you an answer in these many seconds, or it requires this much memory, it requires this much bandwidth, it requires this much energy, depending on the units and depending on the particular setting you are working in. There is a statement about the resource consumption of an algorithm, right, or a computer, any other solution, and that needs to be proven, right? This is a claim, you need to prove it. And there, so especially this data science, the proofs, when you actually talk about proving something about the properties of the algorithm, how it consumes the data structure, how it uses the data structure, it actually in many cases leads to much better solution, beautiful solution, elegant solution, more efficient solutions if you work on the proof of it, right? So, it's extremely important in computer science, and in general also it's trying to make statements like I've been telling you from day one in this course, that a statement, these meaningless statements that we keep on talking and pretend that okay, it doesn't matter. They don't matter maybe because we hear something else, right? I say something, you hear something else, because from the context and stuff. But here we get a training of how to work with precise statements, right? Well-defined notations, right? A precise notation, right? An unambiguous, clear-cut statements and notation, and it just trains you that you cannot exclude a case, right? Remember when we said, okay, one is for all x, p of x true. That's a statement. Now, even if the statement isn't true for x equals negative 17, just one non-true proposition out of these infinitely many, it's not a proof, right? So you get trained to write and talk in a precise language. Okay. So for example, here you must have heard this stuff. The glass is half full, the glass is half empty is a meaningless statement. The glass is always full, right? Not always with water. Half of it is filled with water, and the rest of the half is filled with air, right? So it's never so it's a useless statement when people ask you whether you're a pessimist or an optimist or how do you look at the glass, right? I always tell people I'm a very, very optimistic person. I believe that today is going to be much better than tomorrow, and that's an optimistic statement, right? Yes. It's without defining what is optimistic. Okay. So a proof is an argument that convinces someone of the truth of the validity of a statement, the truth of a statement, right? In mathematics, more technically, a proof is a chain of logical deduction, right? Big words, logical deduction, that demonstrate the truth of a given proposition, right? Assuming the truths of some known statements. These are called axioms, right? So some of these self-evident true statements, these are called axioms. We deduce the truth of our statement from them through a logical reasoning, and I'm going to give you some reasoning, what is called inference rules, right? How do you infer a statement from another statement or a collection of two statements and so on. Okay, so let's get rid of this some terminology. Most of you must have heard this. An axiom is a really basic assumption about some statements, right? Very fundamental statements. We don't have a proof for them. We just assume they are true, right? So I'm going to give you some examples. There is a straight line between any 2 points. There isn't any proof of it. This is not a theorem. It's just an assumption. Okay, we tend to live in a world. We chose to live in a world where this is a true statement, that there is a straight line between any 2 points, right? Now, it needs a definition of straight line, it needs a definition of point, it needs a definition of space, right? So this is a true statement about Euclidean geometry, but one can refine some different rules of geometry where this isn't true, right? 2 is bigger than 1. Well, who said 2 is a symbol, 1 is a symbol? I just chose to call it 2 is bigger than 1. Or in the Peano axioms, we call it this is the next biggest, this is the smallest bigger number than 1, right? Smallest biggest integer than 1. So we chose it, we call it like this, and these are axioms, right? Theorem is what is an important proposition that we actually want to prove, right? So there is a proof of it. A true statement is called a theorem when there is a proof associated with it, right? A lemma is also just like a theorem. It's a statement which has a proof, but generally lemma is used building block to prove a theorem. Okay, so these are perhaps not as important as a theorem statement. When you write a theorem, proof of a theorem, you build up towards you build up the proof. You break down the proof into multiple lemmas, and then you combine the lemmas and reuse it or repeatedly use the lemmas to get the proof of it. Okay, I'm going to give you some examples of this. A corollary also is a proposition, a true proposition for which there is a proof. But we typically refer to a statement as a corollary when it just immediately follows, it readily follows from the statement of a theorem, right? Rules of inference is those rules that makes the justification for a logical deduction step that we take. Okay, and a fallacy is just a flaw, an incorrect reasoning, which is logically not correct reasoning in the steps of a proof or something, right, in a deduction. So here are some axioms of the Euclidean geometry. So this is the Euclid's elements. So one of the first page of that is these kind of statements, right? Any line segment can be extended into a line. You give me a segment, I can extend it to an infinite line, right? Any 2 points can be joined by exactly one line segment, and that's the shortest path, the shortest distance between these 2 points. Given a point P and a length R, I can always draw a circle of radius R around the point P, right? So we say there is a unique circle that is given around this point P of a given radius R. Any 2 right angles are congruent, and given any line and point, I can read exactly one other line parallel to that given line that is parallel and goes through point P. And these kind of statements self-evident. The Pythagoras theorem, we have seen it multiple times, right? So the Pythagoras theorem says, so this is the more geometric version of it, the trigonometric version of this. We will, when we saw the Fermat's last theorem, another statement there was more of number theory statement there. But let's just do the Pythagoras theorem says that the square of the hypotenuse is equal to, for a right angled triangle, the square of the hypotenuse is equal to the square of the base and the square of the perpendicular, right? So it basically says the area of the square made up here, this square area is equal to the sum of the green and the blue squares. Okay, this is a proof of it. Everybody knows there are 19,000 proofs of stuff, and you can prove it. The triangle sum theorem, right? The sum of angles, interior angle of a triangle equals 180, and you can generalize it to any polygon. Okay, some rules of inference, and so this is again just vocabulary session, and then we will actually begin with proof. Rules of inference. The first one is called modus ponens, right? You just some word, a fancy word, very common sense statement that if you know that some statement, some proposition P is true, right? You know it is true. You have a proof of that thing that P is true. And you also know that P implies Q is true, right? So you know the truth of, you're sure you're given 2 facts, the fact that P is true and the fact that P implies Q is true. When you have these two, you can safely conclude that Q is also true. Okay? So why is that? Very simple. We know that P and P implies Q, this whole thing implies Q is a tautology, right? So think about it. When P is true, so this is the P implies Q truth table. When P is true, which rows are we talking about? Which rows are we talking about? The first and the second row, right? We are talking about the second row. Now, in which of these two, out of these 2 rows, which one has the P implies Q true? Only the first row, right? Where P is true and P implies Q is true. So this is basically a summary of this truth table, that if you are talking about the first row, then in the first row Q is true, right? When P is true and P implies Q is true, P implies Q is true. If P happens, then Q. If P is true, then Q is also true. And now I tell you also P is true. So then Q must be true, otherwise P implies Q will false, right? So if P is true and P implies Q, and P is true and Q is false, and P implies Q should not be false, should not be true, right? So this is called modus ponens. P and P implies Q. These are called the hypotheses of this the 2 hypotheses of this modus ponens rule of inference, and this Q is called the conclusion of that, right? So if these 2 together follow, these 2 together imply Q, and this is how it's written. I'm not going to refer to it. I just wanted you to hear these words, so you don't get impressed with this when people don't like impress you with these big words. Okay, modus tollens is another rule of inference, which says that if you know for a fact that Q is false and that P implies Q is true, so then we can conclude that P must be false. So Q is false and P implies Q is true. Together these 2 statements imply that P is false. Okay, this is how it's written, not Q. together with P implies Q, and then both of them together imply that not P is true. P implies Q is true. That means if P is true, then Q must be true. Now Q is false. Then how can Q be false if P implies Q is true? The only way Q can be false is when P is not true. And the condition isn't met. So the condition isn't met, then P implies Q is true, but because Q is false, P must be false, right? Okay. So, and that is, you can see that when P implies Q is true and Q is true, so we are talking about the last row only, right? In the last row, P implies Q is true and Q is false, so then P must also be false. Okay, it's called modus tollens. Then there is a hypothetical syllogism which says that if P implies Q is true and Q implies R is true, then P implies R must also be true, right? So it's kind of some kind of transitivity between implication. Okay, so a little bit about fallacy. If you remember from in the first lecture I gave you a proof of 2 is equal to 1. Let's do another one. This you must have seen, and I'm still waiting for the problem identifying fallacy in that proof. So suppose A equal to B. Okay. So now if I multiply both sides with A, what do I get? A squared on one side and A times B on the other side. Okay. Now if I add A squared minus 2AB to both sides, right? So on one side I get 2A squared minus 2AB, on the other side I get AB plus A squared minus 2AB, right? Adding two things, adding the equal amount to both sides of an equality doesn't change equality. Now this is 2 times A squared minus AB, just taking 2 common from the left side terms, and A squared minus AB on the other side, right? A squared minus 2AB plus AB is minus AB. Now A squared minus AB cancel each other. I can divide both sides with the same number, A squared minus AB, and I get 2 equals 1. Okay. What is a proof? So we know what is the logical thing of what is the kind of a definition of a proof. Logical deduction to demonstrate the truth of a statement, which is a chain of logical deductions from a set of axioms to your given statement that you want to prove, right? That's called a proof. So if you make a claim, here is a very good definition of a proof. Okay, it's from a CMU course, a Carnegie Mellon University. They define a proof to be any statement, any argument that can withstand all criticism by a highly caffeinated instructor or TA. Okay, not you just write something and then you assume it is a proof. A mathematical proof should resemble a simple and clear-cut constellation, not a scattered cluster in the Milky Way. G.H. Hardy was a really strange guy. So here is this is the statement I want to show. Beauty is the first test. There is no permanent place in the world for ugly mathematics, right? When you write a proof, there has to be this thing. I don't know how many of you know proofs from the book. Proofs from the book. No? Anyone? No? Okay. So Paul Erdős, another mathematician for last century, Hungarian mathematician, he used to say that God has a book, the book, in which all the beautiful, elegant proofs are there, but they doesn't give us all at once, right? Give us one by one, once in a while, gives us those things. And then, so they wrote a book about it. It's called Proofs from the Book, in which they tried to collect all the beautiful proofs, right, of some well-known statements, multiple proofs, some of them, 2 of them at least, I'm going to cover today. And the others also are really cool, very simple statements. Okay. So remember, we talked about this thing that finding the truth value of a proposition, finding proofs for propositions, for claims is not necessarily an easy task, right? So this was our way of looking at the Pythagoras theorem then. The Pythagoras theorem says that a squared plus b squared equals c squared have integral solutions. There are 3 integers, a, b, and c, which satisfy this equation, right? We know it's a true statement. Just take a equals 3, b equals 4, and c equals 5, and that's this is true, right? 3 squared plus 4 squared is equal to 5 squared. So, the Pythagoras theorem is an existentially quantified statement, and the proof will only require one example. So, we have an example. No? No, but it says there exists, it has solution where a, b, c are positive integers. It says there exist integers a, b and c, positive integers a, b and c such that a squared plus b squared equals c squared. So, it is an existential statement, right? Existentially quantified statement. How do you prove an existentially quantified statement? Come up with one example. It says there are some, right? There may be more, we do not know. There are many triples of integer which don't satisfy this equation, right? So, 1 squared plus 2 squared is not equal to 3 squared, right? But that does not say. Pythagoras theorem says there exists at least one set of 3 integers, not necessarily unequal. It does not require any of those things, for which this is true. Right. So, this statement is true because here is an example of this, right? Existentially quantified statement is proved by an example. Okay. Here was in this vein, the Fermat's claim that he is the elegant proof, a short proof, where a cube plus b cube is equal to c cube has no integral solution. Okay. So, Fermat claimed that there are no 3 integers. Actually, the statement is about any end, any higher power. So, we basically said that for 2 this works, right? For 1 actually many other things. So, 2 plus 3 equals 5, for a to the 1 plus b to the 1 equals c to the 1 has many solutions. A squared plus b squared plus c equals c squared has some solution. Fermat said that for any n bigger than 2, a to the n plus b to the n is equal to c to the n is not true. You pick any 3 numbers, right? For all a, b, c, this statement is never, this equality never holds for when the exponent of these numbers is greater than equal to 3. Okay? So, this is one version of the Fermat's theorem. A cube, there are no 3 numbers such that a, b, c, such that a cubed plus b cubed equals c cubed, right? We saw this already. It took 350 years to prove the statement. Andrew Wiles spent like 8 years on proving it, 7 years to try to prove it, and he announced a proof in which there was a flaw. For after a year or a few months, it was discovered there was a flaw there. Then it took another year to prove to rectify this the proof, and then announce the final proof that people now agree is the proof of this statement, right? So, it took 350 years to prove a statement. So, it is not easy to prove statement, right? That is what all mathematics is, proving statements, right? So, theorem proving. We also saw the Euler conjecture in the similar vein. Euler also made a very general statement. This is one specific example of that you take any 4 numbers and raise them to the 4th power, 3 of them, the sum of the 4th power of 3 numbers will never be equal to the 4th power of the 4th number, right? We also made this statement about a to the 5, and so we said take any 5 numbers, the 5th power, the sum of the 5th power of 4 of them will never add up to the 5th power of the 5th number, right? So, this is a general statement, but this is, it says no solution, right? In the same way as the Fermat's theorem, the Fermat's last theorem, but it was proven after 200 years that actually it's not true, right? After 200 years, we found one counterexample. Now we know many more counterexamples. With using computers, we just plug in all the numbers, and it turns out that these two, just this a to the 4 plus b to the 4 plus c to the 4 for these values of a, b, and c is actually equal to d to the 4 for this value of d. So, for the Euler's conjecture was a universally quantified statement, and we found one counterexample to that, and that makes it not true. Okay. The Euler conjecture, that is your homework from class 1. It's still an open conjecture. You should give it a try. It's almost close to 300 years. That every even integer greater than 2 can be written as sum of 2 prime numbers. Okay, every integer we tried, every even integer we tried in the last 300 or so years, with any computer, with anything, any very many long digits people have tried, actually they have the sum of 2 primes, but we don't know the proof of it. We either need a counter example, which would be very big numbers, because we've tried many all the reasonably large even integers, but there may be some even integer which is not, cannot be written as a sum of 2 primes. But this conjecture is opened and you should give it a try. Oh, this is a cool one. Okay. So this is a cool computer science a computer aided proof for so called the 4-color theorem. So you take any region, the map of any region, you can color it. In a region there are countries or cities or some sub-regions, right, which have shared boundaries and far away, farther apart. You want to color them, right, so that neighboring regions don't get the same color, right. So if you get, if this region and this region both are the same colored as blue, we won't be able to distinguish which country begins where and which what's the area of one country or what's the area of the green country, right. So we generally, when we we want to color stuff these regions with such that no neighboring regions get the same color. Now that's an easy problem, right. So how many it's a finitely many countries in the world, right. So use a different color for every country, right, or for every region, every city, every town, whatever this is, right. It's easy, it's a trivial problem. The problem becomes interesting when you want to be you want to optimize the number of colors, when you want to be stingy in using the number of colors, right. So the problem, the conjecture, the Kemp's conjecture was, Kemp conjectured it, that any map, as long as it's a 2D map, the regions can be colored with at most 4 colors, right. You only need 4 colors to color this thing. How many different colors are used here? 4? No, there are many, quite a few. So this is different, then there is a brown, the red, the green, the yellow, no, the blue, right. So there are 5 or 6 colors. 5 color is always easy. 4 color, can you do it with 4 colors? Okay, that's the conjecture was you can always do it with 4 color. It's very simple statement, right, very simple statement. The proof is notoriously hard, I mean, somehow. So Kemp announced a proof in 1879, yes? Can you disprove this? No, we have a proof for it. Yeah. So Kemp announced a proof for it in 1879 that, well, we can color it, some elaborate geometry and algebra using use that, and announce that there is a proof for that thing, right. There was another proof given by Tate and a year later, and was a different proof, slightly simpler proof. Unfortunately, both of them had flaws, right. So in a year, the proofs were found to have some flaws. They were not proofs, right. So the problem was open again, right. It took about 100 years to actually somebody announced a proof. Appel and Haken announced a proof of this, the 4-color conjecture, or this is called the 4-color theorem now. That their proof was really cool. So they broke down the proof into statement, and of course using the Hirsch's result, they broke. Okay, so they say for there are different types of maps, right. For some they gave a proof, right, mathematical proof. For others, they wrote a computer program and they checked it, and they actually came up with a constructive coloring of the 4-color. They constructively colored those maps, those classes of maps, with 4 colors. Right now, there was a lot of debate on this, whether it's a proof, it constitute a proof or not. What if the computer has flaws? What if the hardware has a bug? What if their code has bug? What if their implementation has problems, right? What if they cheated? So people did try to check. Nobody has actually verified all the cases, and all nobody has. People tried, but it's very too cumbersome a code, right? And it was 1976. The proof was really. The coding standards were very different then and other stuff. So in 1997, the similar proof, Paul Robertson gave a proof of this thing. Slightly simple computer program, but still a computer aided proof of this, right? So this is UIUC. If you go to UIUC, some of you should go there. In the computer science department, the computer science department is called the 4 color suffices, right? So it's big written, the 4 color are sufficient, and this is the 4 color suffice stamp they issued in honor of Apple and Haken, right? I want to prove P implies Q is true. Okay, so I want to prove basically that P implies Q is true in all cases except for the one case, right? The second row. When is P implies Q false? When P is true and Q is false. Okay, when P is false, what is the value of P implies Q? What, doesn't it depend on the value of Q? Irrespective of the value of Q, when P is false, P implies Q is true, right? The last 2 rows are telling me, irrespective of the thing. The only case it becomes interesting, where it becomes like there could be a problem, is when P is true, because then there is a possibility that if P is true and Q is false, then P implies Q could be false, right? So in a direct proof, I assume P is true, and from that I deduce that Q is also true, right? So meaning I just kind of exclude the possibility. I just want to say that this row, this combination of P and Q never happens, right? This combination of P and Q truth values is not allowed, it's not possible. When P is true, Q cannot be false, right? That amounts to a proof of P implies Q is true, right? When P is false, P implies Q is already true, we are done with that. So when P is true, then if Q is false, I may be in trouble. So I exclude that possibility. Okay. So our goal is just to rule out that possibility that when P is true, Q cannot be false, right? And that will give me a proof of P implies Q. So it's an example. The product of 2 even integers is even. Very simple statement, everyone knows it, right? So let's see where is the implication of this thing. What is an even integer? Huh? Yes, another way to write it. What is an even integer? Huh?
2x.
What is x? Any number is 2x.
X can be any integer.
X has to be an integer. A number is even integer. An integer is even if it can be written as 2 times another integer, right? Any number 4.6 can be written as 2 times 2.3, right? Any number r can be written as 2 times r over 2, but that r over 2 has to be an integer. Okay? So a number is even if it can be written as twice another integer, right? Twice an integer, not another integer, because 0 is even integer because it can be written as 2 times 0, right? That's not another integer other than 0, it's an integer, right? Okay, so now the statement is saying that the product of 2 even integers is even. So we have now words for even numbers. So let's write it. We said direct proofs are used for implication, for proving implication statement, right? P implies Q type statements. Where is the P implies Q type statements here? Can you restate this in terms of if X then Y, if P then Q? If some predicate proposition P, then some predicate Q.
If an integer x is even and an integer y is even, then the product x y will be even.
Yeah.
But if an integer x is divisible by then x is even.
That's a definition of even. No, this is not a statement. Where is the product thing? This is about product. Yeah. So it says if I multiply 2 even integers, I will get an even product, right? So if I multiply x and y and both x and y are even integers, then the product x times y will also be an even integer, right? So if x and y are even integer, then x times y is also an even integer. Okay, let's apply direct proof methods to this, right? What will be a direct proof method? So now we have an implication. What will direct proof method begin with? How would we start? How would we start the statement? What did we say earlier in the previous slide? Yes.
Assume that x and y are even.
And
then prove that q is true, that xy is even also.
yeah, so assume let's assume I multiply two even integer, right? So that will be p. If x and y are even integer, assume p is true. Suppose I have two integer x and y and I multiply them, then q, the product will also be even integer. So I know how to say even integer. So assume that p is true. Suppose x is an even integer, that means x can be written as twice another integer a, and y is an even integer, that means y can be written as twice another integer b. So x is equal to 2a and y equal to 2b. Now if this is true, then the product must be true, right? The product must be even, that q must be true. So how would I argue? What is x times y? What is x times y? X times y is 2a times 2b, right? 2a times 2b is equal to 4 times ab, which is equal to 2 times 2ab, right? If a is an integer and b is an integer, what is a and b? A and b, a times b is also an integer, right? The product of two integer is an integer. So 2ab is also an integer. So now xy can be written as 2 times another integer, right? 2 times an integer, and that's the definition of even number, right? Even integer. So what I got is that 2xy can be written as twice an integer. That means xy is even integer, right? So if I begin with x and y which both even, then the product xy will be even. Okay, very simple, just not there, but it's just wanted to a warm up thing, just so that you get used to restate the statement in the implication form if you want to use direct proof method. Identify what is the hypothesis, what is the conclusion of that implication, and assume that the p is true, the hypothesis of the implication is true. Rewrite it, see what is it, and all we used here that x is even and y is even, right? So that's the 2a multiplied by 2b, right? We used the logically deduced it. Where is the logical deduction from known axioms? We use every step was following the definition of multiplication, right? The definition of the product of two integer is also an integer. Double, if x is an integer, then double that is also an integer, right? And those kind of, we assume those things. So from given those rules and those methods and those axioms, I can conclude that 2 times x times y is also 2 times an integer. Yes, please. The even numbers definition. Okay. An integer y is even if there exists an integer x such that y equals to x.
So we can consider this definition as an axiom.
This is a definition. This is just like a vocabulary thing, not really an axiom. It's a definition. It's a word. It's a notation. It's a symbolic thing.
So should we have to also prove the definition then?
Definition doesn't need to be proved. There's no claim here. This is just redefining my word. When I say even, I mean that a number that can be written as 2 times some other number. Okay, definitions I can define to be something like, so let's say let C be a cup, C is blue. So C is blue, I need to prove. I don't need to prove to you C stands for the cup. I just said C stands for the cup. Okay. Okay. Okay, so we given that if p is true, then q must be true. If x and y are even, then x, y must be even, right? And that, so we conclude if p is true, then q is true, implying that p implies q is true. Okay, all of the story of the truth table should come here. We said, okay, if it's the bottom 2 rows of the truth table, we don't care because p implies q is already true. We are done with that case, right? If of the first rows, when p is true, then the second row is not possible, right? When p is true, q cannot be true. So the second row thing is not possible. And that's the second row is the only one when p implies q could be false, right? So now p implies q cannot be false because the game is between either the first row or the third and the fourth row. Okay. Okay, so here is another one which is already broken. If a is bigger than 3 and b is bigger than 4, right, A and B could be any number, right? Don't have to be integer. Then A plus B is bigger than 7. Could it happen that somebody has more than 3 rupees and another one has more than 4 rupees and together they have less than 7? Right? This will not happen. So, how would you prove that? What is the, we know what is P, what is Q, we are applying direct method, a direct proof method. So, we will assume P is true. Suppose A is some number, the only condition, the only property of A I am going to use is that it is bigger than 3, because I assume P is true, right? And and simultaneously B is also bigger than 4, because P is A greater than 3 and B bigger than 4, both of them must be true. So, if P is true, meaning A is bigger than 3 and B is bigger than 4, right? Then if I add these two inequalities, what do I get? I get A plus B, the equalities. Now, this, how can we do these things with equalities, inequalities, inequality? How can we add? Then those are from the axioms, right? From the rules of mathematics or something, right? That if x is bigger than y and A is bigger than B, then x plus A is bigger than y plus z, right? Or whatever I said there, okay? Plus A is bigger than y plus b. So, A plus B then is bigger than 3 plus 4, right? 3 plus 4 happens to be 7. So, I got that A plus B is bigger than 7. So, I can conclude that if A is bigger than 3 and B is bigger than 4, then A plus B is bigger than 7, right? Notice this thing. This is really the holy grail for a mathematician. When we write this, we are very happy. Okay, what does it stand for? It's like end of proof, but it stands for something. QED. What is QED? In LaTeX, you write /QED. It will put this box on the right side. What does QED stand for? Huh? So, QED basically stands for, so this is what we needed to demonstrate, right? Something like that. I forgot what is the actual statement. Okay, let's do an example, an exercise. Now, I am making a statement which may or may not be true. Okay, the product of two consecutive integers is an even integer. Can you first make it the statement into an implication type statement? What is an implication statement for this? What is the implication? Make this statement in terms of an implication. Yes. Okay. If B is equal to A plus 1, then okay, so B is equal to A plus 1, so then A times B. So, wouldn't it be like then A times B? B is equal to A plus 1. So, okay, so A times A plus 1 is equal to, is even to, what is A? Integer. So, for all integers, A times A plus 1 is equal to an even integer, right? Yes, that's, you can substitute the word even for the word 2 times x, where x is an integer. Okay. So, prove that the product of two consecutive integer is an even integer, right. So, if two numbers are consecutive integers, then their product is an even integer. That is the statement, right. So, if I multiply so any two consecutive integer, let us call one of them A and the other is A plus 1. One of A or A plus 1 must be even integer, right. That is how even and odd numbers are interleaved between them, right. It is alternating odd and even. So, one of them, either A or A plus 1, has to be an even integer, right. So, let us say A is even. Okay, for without loss of generality, assume that A is an even integer. So, even integer meaning it can be written as 2 times m or 2 times x, right. So, one is even, the other is, it may be successor or the predecessor, right, maybe the previous one or the next one, the consecutive integer, that will be odd, right. So, the other will be 2m plus 1 or 2m minus 1, right. Now, if I multiply 2m with 2m plus 1, what do I get? 4m squared plus 2m, right? And if I multiply 2m with 2m minus 1, what do I get? 4m squared minus 2m, right? So, in both cases I will get 2m into 2m plus minus 1, it will be 4m squared plus 2m or minus 2m, right? In either case I can take the 2 common, and the product of these 2m and 2m plus minus 1 plus or 2m minus 1 can be written as 2 times another integer, right? If m is an integer, then 2m plus 1 is an integer and 2m minus 1 is also an integer, right? Odd or even, that is not my concern, but this 2m times 2m plus minus 1 can be written as 2 times another integer, and that means that is a definition of even number, right? So, I can write that the product of 2 consecutive integer is an integer, is an odd integer. Is this clear? Yes? Okay. Let us do another example. The sum of 2 rational number is a rational number. Yes? Yes, this is true for all integers, right? So, 0 multiply with negative 1 you get a 0, or you 0 multiplied with 1 you get a 0. There is no counter example. What is 0 times 1? What is 0 times 1? Which is an even number, right? So, there is no counter example. What is 0 times negative 1? Which is an even number, right? What is not even? The product of 2 consecutive integer is not even, yes? Then how do you select 0? You have some, so if you want to go in that direction, let us say you have some consecutive integer whose product is not even. Now, you can't now select 0, you have to go with those 2 things, you have to find that those 2, that you claim there exists a counter example to that statement, that the product of 2 even integer is even, 2 consecutive integer is even. No?
My only reasoning was if it's not even, then it's odd. Let's say that we start with this.
If it is not, going to just please say proper words. What is this it refer to? The product of some 2 consecutive integer is not is odd. Okay.
And then we say produce 0 as a candidate, 0 as a candidate number.
Candidate for what?
That will disprove that it is odd. If it is proven that it's odd, then it must be even.
You cannot bring in. So, you see, so you say, if you make a claim, stop phone please. If you claim, so here is it, I claim whenever I multiply any 2 consecutive integer, I get an even answer, right? The product is an even number, right? If you want to disprove me, if you don't agree with the statement, you will say, no, I know 2 consecutive integer whose product is not even. And you have to begin with those 2, those consecutive integers. Now, 0 is not a thing, because 0, I just said 0 times 1 is even, 0 times negative 1 is even. So, if in that consecutive pair 0 is involved, I am done, I proved it. There may be some counter example. Then you have to argue about the structure of those 2. Why did they give you odd number? There cannot be any counter example, because we just proved the theorem, right? Yes.
He's talking about assuming that it's not odd and then proven by contradiction. So
that will be a different thing. No, but he was that is a different thing we will talk about. But he said that 0 could be a counter example. So, it is a good idea to check statements may break down at the boundaries, right? It is some special situation, because 0 is a really strange odd integer, right? It is a really unique type integer, neither positive nor negative. There may be something there. So, you check it. So, okay, we will see. And okay. So, next thing we want to prove with the sum of 2 rational numbers is a rational number, right? When you add up 2 rational numbers, any 2 rational number, then you will, the answer you will get, the sum you will get will also be a rational number, right? The first thing we need to do is just substitute the word rational, try to find a proper description, proper notation for the word rational, which we know already. In implication form, it says if I add any rational number p with any other rational number, not any other, any rational number q, then p plus q is also a rational number, right? Now substitute the rational number. So let's say p is a rational number 1/3, right? Is 1/3 a rational number? Because 1 is an integer, 3 is a non-zero integer, the denominator and numerator both have to be integers, and the denominator is not allowed to be 0, right? So p is 1/3, q is 3/4. If I add them, what do I get? What is the sum of these two rational numbers? What is p plus q? P plus q is you take whatever the LCM or the common denominator, and then you whatever you do, right? So it's equal to 13/12. Is 13/12 a rational number? Why is 13/12 a rational number? 13 is an integer and 12 is an integer, and 12 is not equal to 0. These three conditions make it a rational number. So we conclude that p plus q is a rational number, right? So we conclude that when I add two rational numbers, I get a rational number, right? Is it a proof? Why not? This is an example, right? This proof only works when p is 1/3 and q is 3/4, right? This is the only time, this is the only example will work, right? If I ask you to write a computer program to add up rational numbers, you can't just hard code the number 1/3 and 1/4 and 3/4 and give me an answer for that, right? It has to work for, your code has to work for all rational numbers, right? So this isn't a proof, but it is a good example. We tried it and we convinced ourselves that statement seems to be true, right? So let's try the proper proof. So let p be some general rational number a over b, right? Where a is an integer and b is a non-zero integer. So let's say p is a over b and q is a over b, where a is an integer and b is also an integer, but b is not 0, right? So now it's a proper general rational number p, right? So what is p plus q? What is a over b plus a over b? Just, what is a over b times a over plus a over b? What is a over b plus a over b? 2 times a over b, right? So b is the LCM or whatever you do. If a is an integer, what is 2a? It's also an integer, right? If b is a non-zero integer, then the denominator here also is the same b, so it's a non-zero integer. So we conclude that p plus q is also a rational number, right? Yes. Yeah. So it is not a proof, because p and q are, this only proves if p and q are two rational number who are equal, then their sum is equal to is also a rational number, right? So this works for many examples, for infinitely many examples, for different a's and different b's, but it doesn't prove the statement. The statement says any rational number added with any rational number must give me a rational number, right? This isn't a proof. Is this clear? Okay, so let's do a proof. Let's say p is a over b, right? Some rational number with a is an integer and b is a non-zero integer, and q is some c or d. C may be equal to a, c and d may be equal to a and b respectively, right? They're allowed to be equal. So q is some rational number c over d, where c is an integer and d is a non-zero integer, right? Now what is p? Is p a fraction? It's a ratio between two integers, right? Is q a fraction? Yes. It's a ratio between two integers. So if I add two fractions, what do I get? I get another fraction, right? So p plus q, if p is a rational number and q is a rational number, then p plus q is also a rational number, right? Yes?
So is the sum of fractions is a fraction?
Yeah, that's a true statement. Sum of fraction is always a fraction. That's true. Yeah. P. So just do what a fraction a over b plus c over d is always equal to this is an integer. This is an integer. If b is not 0 and d is not 0, then b times d cannot be 0. So the sum of two fraction is always a fraction.
But if the defined fraction Then why does this theorem need to be proved? Because it automatically means the same thing.
No, but if you define now we are this is what's called the closure operation. We are saying that rational numbers are closed under addition. When we add two rational numbers, we stay within rational numbers, right? So this is, we still need to prove it. This is not a proof. This isn't a proof. What's wrong with this proof?
Rational numbers are not just fractions because
Rational.
all fractions are rational numbers.
Yeah. So what's wrong with the proof?
Because we define rational numbers incorrectly.
We defined rational numbers incorrectly. No, we defined them correctly. We defined.
Isn't the proof self-referential? Doesn't it just refer to itself? It uses itself to prove itself.
No,
We're trying
it doesn't.
that the sum is rational, and then we
The sum of rational number is rational. Now we are using a fact that the sum of fractions is a fraction. That's a true statement. It's not the same statement.
So don't we need to decompose it back to p plus q?
No, this is some integer divided by another integer. So the mistake we made is that we used kind of the wrong notation for rational numbers, right? Wrong. A rational number is a fraction. Every rational number is a fraction, but every fraction is not a rational number, right? Is pi over 1 a fraction? Pi over 1 is a fraction, right? So if I add two fractions, I could be adding pi over 1 plus pi over 1. What do I get? I get 2 pi over 1, which is not a rational number, right? It's not an integer divided by another integer, right? So we used fraction, so this is not the right thing, even though this thing is the right proof actually. So let's see, let me try to do another thing. Yes.
सर पिछली स्लाइड में हमने एक एग्जांपल देखी थी 1/3 जो प्रूफ बाय एग्जांपल थी.
Yes, this was not proof by example. There is nothing called proof by example, right? Yeah.
तो सर 1/3 को हम रैशनल क्यों कंसीडर करें? Isn't it like 0.infinitely 3 is a very irrational?
No, rational number का definition होता है ना. The definition is that there is if you can write a number is an integer divided by another non-zero integer, then it's called rational number. I never said infinitely many digits or I don't know, truncating sum or whatever these things are called. That's not the definition. Okay, okay. So let P be. So this is what we did. Let P be a rational number. That means it can be written as A divided by B, where A is an integer and B is a non-zero integer. Let Q be a rational number, where it can be written as C divided by D, where C is a real an integer and D is a non-zero integer. They could be the same. Some of them could be the same. We don't know. So now if I add P plus Q, it amounts to adding A over B plus C over D. Adding A over D plus B over C is actually this thing, right? AD plus BC divided by BD. Now what is AD plus BC? It's an integer, right? It's the product of two integers added to a product of another two integers, and that's an integer, right? Sum of integers is integer, and the product of two non-zero integer is going to be a non-zero integer, right? If none of them is 0, then BD cannot be 0. So P plus Q is a rational number. What's wrong with this proof? Nothing? Okay. So there's nothing wrong with this proof. I mean, I can't make infinitely many wrong proofs. So what did you learn from this? What did you learn from this? This proof by example is not a thing. Okay, you have to be careful. You have to cover. You have to remember that original the way of thinking, the way of talking. That's where you learn from doing proofs. That you know, you have to write, you have to make sure that it works for all cases. You have to make sure that doesn't mean just you works for infinitely many cases doesn't prove it, right? Because it could be in the statement could be true for infinitely many statements, but only one counterexample will disprove the statement. Okay, okay. So let's do this thing. Again, this may not be even true because I am asked you to prove or disprove. Now, the product of any two odd integer is an odd integer. Okay, just don't jump to the paper, please stop. The product of any two odd integer is an odd integer. Suppose you think that this is not true. You want to disprove this claim. What will it amount to? What will it take to disprove this thing? One example of what? Yeah, so you just come up with any two odd integers, any two, one example, one pair of odd integers, which when multiplied give me an even integer. That will disprove the statement, right? I don't know if it is true or not, so whatever you think, but if you want to disprove it, you have to look for counter examples. If you want to prove it, now you have to come up with the reasoning, with a logical argument for that. So how would you prove this? Again, try to state it in terms of an implication. If I multiply two integers x and y, where x is an odd integer and y is an odd integer, then the product x times y is also an odd integer, right? So let's say I take two odd integers, one is 2m plus 1, this is the definition of odd integers. Any odd integer can be written as 2m plus 1 for some m which is an integer, and 2n plus 1 where n is some other possibly equal to m or maybe not equal to m. So one odd integer I call 2m plus 1, the other odd integer I call 2n plus 1. Multiply them, what do you get? You get 2m plus 1 times 2n plus 1, which is equal to 4 times mn plus 2 times m plus 2 times n plus 1, right? In the first three terms, take 2 common out, you got 2 times some integer. If m is an integer, n is an integer, then 2mn is an integer, plus m is another integer, plus n another integer. This whole thing amounts to an integer. So I can write the product of 2m plus 1 and 2n plus 1 is 2 times some integer plus 1, right? 2 times some integer plus 1 is the definition of odd integers. Yes? You can do that thing, still this will work. Okay. So prove or disprove that the product of any 5 consecutive positive integer is divisible by 120. Yes?
So basically we are going to take when we take 2m and 2n to be two even integers, right?
Yes.
So we're taking them from after proving first that that multiplying an even number, an integer by 2 actually gives us an even.
It's a definition. No? We're not proving or we're not using. It's a definition of odd number is, what is an odd number? Any number that can be written in the form of 2 times an integer plus 1. That's a definition of odd number. That's just the word odd number stands for this. An integer is odd if there is an integer m such that 2 times m plus 1 is equal to this number. Yes.
So can we just consider this to be an axiom then? Because it's
What is an axiom?
It's the assumed truth. That we
Assume what true?
It's something that we basically build our further proofs on, but it's like the building.
No, no, no. Which one of these things you want to be an axiom? Not what is an axiom. The definition is not an axiom. The axiom is a proposition. This is not a proposition. It's not supposed to be a true or false thing. It is a translation. It's just a language vocabulary I'm setting up. Okay, just like spelling things in some other thing. Just like I will call this color red. It's not a proposition. It's not up for proving or disproving or disputing or claiming. I just call this, my name is Imdad. That's not up for proving. Right? I chose to call myself Imdad. That's it. See what I'm saying? It's just setting up words, vocabulary that doesn't need to be proved. Right? That is just a state. You have to stay consistent, right? Like somebody asks, what if I think of, I define even number, odd numbers as some number that can be written as twice an integer minus 1, and that's an equally good definition. This proof and all the mechanics of it will change slightly. Then there will be 2m minus 1 times 2n minus 1 multiplication, right? That is not up for discussion, whether what is odd integer or what is even integer. Okay, prove or disprove that the product of any 5 consecutive integer is 120. Again, first try to convince yourself if it is a true statement. Is it true? Let's try it. What is 0 times 1 times 2 times 3 times 4? That's 5, right? What is it? 0. It's 0. Huh? Oh yeah, sorry. So what is 1 times 2 times 3 times 4 times 5? It is exactly equal to 120. What is 2 times 3 times 4 times 5 times 6? Yeah, it's 120 times 6, right? What is the other thing? Well, I don't want to go more. 720 times 7 divided by 2, right? Because the 2 will go out, and that will be 720 times 7 divided by 2. Okay, so you can do it later. Okay, so this seems to be a true statement. How would you go about proving it? What is an implication form of it? Yes. Just let's first do the linguistic thing, rephrasing thing in terms of implication, then we'll see. Yes, that's great. So you say for any integer n, this is the statement, okay, rephrasing of the statement. Take any integer, actually positive integer, right? Any positive integer n, then n times n plus 1 times n plus 2 times n plus 3 times n plus 4 is k times 120. This is the statement, okay? The product of any 5 consecutive positive integer n times n plus 1 times n plus 3 times n plus 4 is equal to 120 times k for some integer k. Remember, any number can be written as 120 times k if k is allowed to be a real number, right, non-integer. But only multiples of 120 can be written as 120 times k for k an integer, for an integer k, okay? Okay, so yes, go ahead now. How do you want to prove?
We just have to show that the product is divisible by is a factor of 5, 4 and 3. And because we have 5 consecutive numbers, one of them will
Good.
always be a...
Yeah, okay, so let's just maybe, I'm going to building up your proof, but I'm starting from a simple thing. Do you think the product of these 5 integers, 5 consecutive integer, is going to be even or odd? So I'm just, as you started from 5, I'm starting from 2. Is it going to be even or odd? Why even? Sorry? Two times what? No, but don't make your life difficult by just. Yes, so in these 5 consecutive positive integer, because in any pair of, in any 2 consecutive positive integer, one of them will be even. So in 5 consecutive, many will be even, right? How many will be even? At least how many? There will be either 2 even numbers or 3 even numbers. So when I multiply all of them, this factor of 2 is going to be there, right? It will be 2 times something times something times something. So the end answer will be 2 times something, right? And that will be an even integer. Okay, so we do this. So we know this is going to be closer to being a multiple of 120 because at least the product is going to be an even number, right? Now, will it be actually a multiple of 3? The product even means it's a multiple of 2. Will the product of these 5 consecutive integers be a multiple of 3? Why? Yes. No, 120 is not a thing. Now we cannot begin with 120. That's what we want to prove. You cannot take that for granted. You have to start from 5 consecutive integers, positive integers. Yes. Okay, so in every 5 consecutive integer, there must be at least one multiple of 3. Yes, because if any integers, if I look at any 3 of them, one of them must be multiple of 3, right? Any 3 of them must, one of them 3 consecutive, and one of them must be multiple of 3, because every third number is a multiple of 3, right? So in these 5, at least one must be a multiple of 3. So we got that the product of these 5 must also be, in addition to being a multiple of 2, it will be a multiple of 3 also, right? In the grand product, there will be 2 times something, but and there will also be 3 times something, right? So it will be basically a multiple of 6. any product of 5 consecutive integers must be a multiple of 2 and 3 simultaneously, which means it must be a multiple of 6. Okay? We can similarly argue that there must be a multiple of 4. Right? The product must be a multiple of 4 because in any 4 consecutive integer, 1 is a multiple of 4. Right? In any 5, there could be more multiple of. Can there be in these 5? Can there be more 3 multiples of 4? Can there be 3 multiples of 4? No, no. 3 multiples of 3, 2 multiples of 3. Yes, because if I get 3, 4, 5, 6, and 7. You see both 3 and 6 are multiples of 3. Okay. How many multiples of 4 must be there at least? At least 1. Can there be more? Yes. Could be 2, 4, 5, 6, 7, 8. This is important. Okay. And there must be at least 1 multiple of 5. That is where we start. Right. So, in these 5 integers, these 5 consecutive integers, at least 1, exactly 1 will be divisible by 5. Yes, there cannot be more than 1 divisible multiple of 5 in these 5. There will be at least 1 multiple of 4, right? There will be at least 1 multiple of 3. There will be at least 1 multiple of 2 other than the multiple of 4. Okay, so you can say that there will be at least 2 multiples of 2. None of them is a multiple of 3 or a multiple of 5. So, there is a unique thing. So, I got this in this product, I got a multiple of 2, I have different multiple of 2 and as a distinct multiple of 3, a distinct multiple of 4, especially distinct from the multiple of 4, right? Because, so look at 12, that is a multiple of 4 and it is also a multiple of 2, right? So, if I use the factor 4 from there, then I cannot use the factor 2 separately. Right. So, now this should be clear to everyone. If I multiply these things, the 5 will be there, 2 2's will be there, then a 3 will be there, a separate 2 will be there, and these 4 different factors will be there, and that factor multiplied by something will be actually a 120 multiplied by something, and that is a multiple of 120. Okay. It is not really a different method for proof, but it's you know, just like when we run a computer program, sometimes we write a different program, right? And sometimes we modify the input. We just pre-process the input, the change the argument, and so that the previous we call this is called reduction of using software reusability, right? Use some software for some different problem. So, this amounts to essentially that thing. We rephrase the statement. So, in terms an implication equivalently by its contrapositive, and then apply the direct proof to the contrapositive of that, right? It's we know the contrapositive is equivalent to the statement implication. So, a proof is a chain of logical deduction to prove the truth of a proposition, assuming the truth of some known axiom. So, we so far saw direct proof of implication P implies Q. What do? We assume P is true, and then we say that Q, in this case, when P is true, then Q must be also be true, right? Then Q cannot be false. So, for implication proof, remember P implies Q is the same statement as not Q implies not P. The contrapositive of a statement is equal to the statement itself, an implication statement. So, here to prove P implies Q, I apply the direct proof method that we learnt in the previous slides to the contrapositive, right. So, I assume not Q is true and then prove that then not P must also be true, right. So, this proves that not Q implies not P is true, which is exactly the same as that P implies Q. Okay. So, here is a statement: if A plus B is bigger than 7, then either A should be bigger than 3 or B should be bigger than 4. Let us see if you want to prove it direct proof, right. Just as a thought experiment in English language, try to prove these things, this statement directly, just so that you see the need of this linguistic trick, this rephrasing a statement and then applying direct proof, right. So, let us try to apply direct proof to this thing. Can you get a handle on this thing, and like a proper handle on this? So assume, so think of arguing with a 5 years old and proving that thing to him or her, that's a 5 years old kid, that if two people together have more than 7 rupees, then either one has more than 3 or the other has more than 4. It's the same statement as we proved earlier, but very similar statements we proved earlier, but it's kind of cumbersome to just, you can't, at least I cannot get a good handle on writing this statement, right. So, let us see what is the contrapositive of this statement. The contrapositive is that if not q is, what is not q? The negation of a greater than 3 or b greater than 4. The negation of a greater than 3 or b greater than 4, right. What is that? We will apply the De Morgan's law, and that is the negation of a greater than 3 and the negation of b greater than 4, right. So, if a is less than or equal to 3 and b is less than or equal to 4, then not p is that a plus b is less than or equal to 7. Is this clear? So, not p is easy. So, this is the statement we want to prove, right, if the negation of a greater than 3 or b greater than 4. So, let us assume direct proof would mean I want to prove if a then b, I will prove, suppose a is true, then b must also be true, right. So, I will say suppose not q is true, right, meaning, or suppose q is false, is equal statement, right. Suppose not q is true, meaning that the negation of a greater than 3 or b greater than 4 is true, right. So, if this is equivalently saying by the De Morgan's law that if a is less than or equal to 3, that is not a greater than 3 and not b greater than 4, which is if a is less than or equal to 3 and b is less than or equal to 4. So, if q is not q is true, this means a is less than or equal to 3 and b is less than or equal to 4. Then not p is true, then a plus b is less than or equal to 7, right. So, let us add both sides of this inequalities. What do we get? If I add both sides of this inequality, what do I get? A plus b is less than or equal to 3 plus 4, right. Same inequalities, you can add both sides, on the other side you get this thing, right. A plus b is less than or equal to 3 plus 4, right. A plus b is less than or equal to 3 plus 4 is actually the negation of a plus b greater than 7, which is equal to not p. So, I proved that if not q is true, then not p is also true, which is exactly the same as proving that if p is true, then q is true. Okay? Yes, please. Where? This one? Okay. So, what is the negation of a greater than 3? A is not greater than 3 means what? A is either equal to or less than, right. So, that is the proper negation. False, it is the same statement, cannot be, statement is either true or false, right, cannot be false. Direct methods is cumbersome to write this whole thing. Okay, I am going to give you more examples where it is actually. Okay, so, we conclude that not q implies not p is true, or equivalently p implies q is true, because not q implies not p is the same as p implies q. Okay. Okay, let us see is another one. I want to prove if the fifth power of a number is negative, then the number must be negative. If you multiply a negative number with itself 5 times, what do you get? Yes. If you multiply a negative number with itself 4 times, what do you get? Yes. So, that is easy power, but now this is the other way around. Not as cumbersome as the previous one, or maybe slightly more than that, I do not know, if your choice. But if the fifth power of a number is negative, then the number must be negative. Can you prove it? So, it would amount to arguing about the fifth root of x, right, x to the 5. The fifth root of, if a number is negative, so what this statement says, that the fifth root of a negative number is negative number. This is what this says, right? The fifth root of a negative number is negative number. That's the statement. This exactly is that statement. The other statement that I earlier said, that if you multiply a negative number with itself 5 times, what do you get? You get negative. So that says the fifth power of a negative number is a negative number. That's not the same statement as this. It's a, okay. So one is arguing about the power, and one is arguing about the square root, the root of that, right? Not the square root, but the fifth root. Okay. So this is also very difficult to prove with the direct method. I mean, not difficult to prove. We are going to prove it in its equivalent, but just arguing about the fifth root of stuff is not easy, right? I mean, we don't have enough language. What is the contrapositive of this statement? So this statement says the fifth root of a negative number is negative. What will be the contrapositive in this terminology?
If x is positive, then the fifth power of x will also be positive.
Yeah, the fifth power of a number, a positive number, a non-negative number is non-negative. That will be the contrapositive, right? So if x is non-negative, then x to the fifth power is also non-negative. Yes? If x is not greater than or equal to 0, then x to the 5. That's his equivalent statement between these two are just exactly the same statement, right? Now, fifth power is just multiplying the number with itself 5 times, right? So if x is greater than or equal to 0, means x is either greater than 0 or equal to 0. If x is equal to 0, is this statement true? Why is this statement true? The fifth power of 0 is what? 0, right? It's 0 times 0, 0 times 0 multiplied with itself 5 times, which is still 0. But if x is negative, if x is positive, then what is the fifth power of the positive number? Is it positive or negative? Why positive? Because if you multiply a positive number 5 times to itself, you will get a fifth positive number, right? Or you multiply any 5 positive numbers, you will get a positive number, right? So assume we are applying direct proof to the contraposition, the contrapositive of the statement. That means assume the hypothesis is true. So if assume x is greater than or equal to 0, then I have to prove that x to the 5 must be greater than or equal to 0, right? So x greater than or equal to 0 means x is either 0 or greater than 0, strictly greater than 0. So if x is 0, x to the 5 is equal to 0, which is greater than or equal to 0. So I am done at least in one case, right? The other case, if x is positive, then the product of 5 positive numbers, same number or 5 different numbers, the product of 5 positive numbers is going to be positive, right? So if x is greater than 0, x to the 5 is greater than 0. Okay. So we conclude that not q implies not p is true, that if x is less than or equal to 0, then x to the 5 is less than or equal to 0, which is equal to the statement that if x to the 5 is negative, then x is also negative for any x. Okay. Okay. So let's see, prove for all positive integers n that if 5 does not divide n squared, then 5 cannot divide n. Can you say this in terms of multiplicity? What does it say? If n squared is not a multiple of
5.
then
N is not a multiple of 5.
then its square root is not a multiple of 5, right? If a number is not a multiple of 5, then its square root cannot be a multiple of 5. Okay. What is the contrapositive of this statement? So first, very mechanical contraposition. What is the contrapositive? If the negation of this, then the negation of this, right? So say that if 5 divides n, then 5 divides n squared, right? That's a contrapositive of this implication. For all integers n, for all positive integers n, if 5 divides n, then 5 divides n squared. That's the contrapositive of this. Okay. So if 5 divides n, meaning if 5 is a if n is a multiple of 5, right, then n squared is also a multiple of 5, right? Let us apply a direct proof to this. What will be a direct proof of this? Assume that n is a multiple of 5, right. Assume n is a multiple of 5, then n is a multiple of 5, just substitute this word, n is equal to 5 times a, 5 times m, right, and then 5 times x or whatever we say, and then n squared is also a multiple of 5, right. So, if n is a multiple of 5, this is a shorthand way of writing n is a multiple of 5, right, k is an integer. So, then what is n squared? It's 5k times 5k, which is 5 squared times k squared, right. 5 squared is 5 times 5 times k squared. Now, what does it see? What do you see here? This number is 5 times 5k squared. If k is an integer, then k squared is an integer, 5 times k squared is an integer. So, this last number is 5 times an integer here. 5 times an integer is what? These are actually another word for it is multiples of 5, right. So, if n is a multiple of 5, then n squared is also a multiple of 5. Okay. So, if n is a multiple of 5 and n squared is a multiple of 5, which is the contrapositive of our statement? Make sense? Okay. So, let us do one more. This is also I try to choose examples where you will actually feel that the need of actually using contrapositive, because it's equivalent, but it's cumbersome to write about to prove the statements directly. Okay. The square root of an irrational number is also an irrational number. If a number is irrational, then its square root is an irrational number, right. So, pi is an irrational number, square root of pi should also be an irrational number. Now, applying square root to an irrational number is just really not going to give you a handle, right, a proper way of control on the statement. So, what is an implication statement here? Can you make an implication statement? Sorry? If then the square root of x is also a irrational number, right. So, if r is generally for r we use r. If r is irrational, then square root of r is an irrational number. Okay? That is the statement given to us. It is very hard to prove it. I mean, it is very hard to argue, to write about the statement. The statement is true and we are going to prove it in a minute, not hard to prove it, but it is just hard to write about it, right. It is complicated. What is the contrapositive of this statement?
So, if square root of r is a rational number, then r is.
If square root of r is a rational number, then r is a rational number, right. That is a contrapositive of this. If square root of r is rational, then r is rational, right. Let us apply a direct proof to this. How would a direct proof start? Assume that there is some number, the square root of r, which is rational number, right. Now, substitute for rational number the definition, right. Assume square root of r is a rational number, that means square root of r can be written as x divided by y, where x is an integer, y is an integer and y is not 0, right. Now, what will you do? I have to argue about some property of r, which is the square of the square root of r, right. So, I would square of a rational number is a rational number, that is the statement now. The square of a rational number is rational, that is what we need to prove.
So, instead of saying r equals to x by y, why can't I say r equals to x squared by y squared?
Yeah, we can say that. We can say that, you can x squared or y squared or whatever you want to write, but we are going to square now. So, then because we are going to, you said r is equal to x squared or y squared. Okay, you can say that, but we will see in a minute why, if you had done that, what would happen. Okay, just give me 1 second. So, what shall we do now? I know something about square root of r. I want to argue something about r. So, I should bring r into the equation, right. How would I bring r into the equation? Square both sides of square root of r is equal to x y, right. So, now we get r is equal to x squared over y squared. Now, if I had taken your suggestion and assumed that square root of r is x squared over y squared, then it would be r is equal to x to the 4 divided by y to the 4. It is a true statement, but why make my life difficult? Okay. So, r is equal to x squared divided by y squared. Now, if x is an integer, what is x squared? And if y is an integer, what is y squared? If y is not 0, then what is y squared? So, also non-zero integer, right. So, I can if you can express r, the square root of r is x divided by y, an integer divided by a non-zero integer, then I can express r is a integer divided by a non-zero integer, namely your numerator square and your denominator squared, right. That is how I would do it. And now I got that if r is rational, if square root of r is rational, then r is also rational, right, which proves my statement, which is the contrapositive of the equivalent rephrasing of our original statement that we wanted to prove. Okay. So, if you want to argue about irrational number, generally going to be very difficult. So, you should do think of contrapositive always. So, prove that for any number n, any integer, any positive, any natural number n, if n squared plus 3 is an odd number, then n must be an even integer. If n squared plus 3 is odd, then n must be even. The statement clear? Do a few examples. What does it say? You do a few examples. What is 2 squared plus 3? 7. So, it says because 7 is odd. So, then what is 2? Even integer. What is 9 plus 3? Huh? 9 plus 3 is 12. So, that is not an odd integer, right. So, I do not need to argue about that. And if so 9 plus 3 is 3 squared plus 3. So, what is 4 squared plus 3? 16 plus 3 9, right. So, 16 plus 3 19. So, 19 is an odd integer, then 4 must be an even integer. So, these are the type of statements this is making, right, for any n. How would you prove this? You see how hard it is to come up with example 19 is 16 plus 3. So, what is the contrapositive of this statement? If n is odd, then if the not q, q is the after then part, the conclusion of the hypothesis, the implication. So, if not q, if n is not even integer, meaning if n is an even integer, then n squared plus 3 is not an odd integer, meaning n squared plus 3 is an even integer, right. So, if n is odd, then n squared plus 3 is even. This is the statement equivalent. Now, this is quite easy, right, because again it does not involve any square root or any anything, right. So, if n is odd, just rephrase it, just rewrite it, just be more precise, just substitute for the word odd. Let us say n is equal to 2 times a plus 1 or 2 times k plus 1 or whatever, right. It is an odd number. So, 2k plus 1, then what is n squared? N squared is 2k plus 1 whole squared, which is 4k squared plus 2 into 2k plus 1 squared, right. So, 4k squared plus 4k plus 1. N squared plus 3 is 4k squared plus 4k plus 1 plus 3, right. 1 plus 3 is another 4. So, I can take 4 common or I can take 2 common. I get that it is 2 into 2k squared plus 2k plus 2, right. What is this? This is an this is an integer. The inside thing is an integer, right. When k is an integer, 2k squared plus 2k plus 2 is also an integer. So, I can write n squared plus 3 is a 2 times some integer. That means n squared plus 3 is an even integer. Okay. Okay, that is it. So, we will talking about proof by contradiction tomorrow.